Okay, hello everybody. We are ready to move on with the first paper session today. I will be chairing this session. My name is Jan Novak. I work for NVIDIA, and this session focuses on path guiding techniques. Each of the three papers that we will hear about addresses path guiding or proposes path guiding in a slightly different context. We have the first paper focusing on product path guiding, and the second paper is more in the context of real-time path tracing, and the third paper will be about path guiding for caustics in movie production. And so we will start with practical path guiding, practical product, I should emphasize, practical product path guiding using linearly transformed cosines, authored by Stavros Diolatzis, Adrien Gruson, Wenzel Jakob, Nowrouzezahrai, and George Drettakis. The authors are from Université Côte d'Azur, INRIA, McGill University, and EPFL. And Stavros was kind enough to record the presentation, which we will watch in a moment. I would like to encourage you to post your questions in the Rocket channel, which I will then deliver to Stavros after we watch the video. So let's go on.
Hello everyone, and welcome to the presentation of our work named Practical Product Path Guiding using linearly transformed cosines. Let's start with a bit of motivation behind our work. Given a virtual scene, path tracing can be used to render photorealistic images, such as this one. But even with state-of-the-art hardware, rendering can take up to several hours, and as such, various reduction techniques are of great significance. One such powerful tool is importance sampling. Looking at the reflected radiance of the rendering equation, we can see the main factors according to which we can import a sample. Sampling according to the BSDF and the cosine factor is used widely, since the BSDF distribution is locally available during path tracing. And for that reason, we can use it to generate samples analytically. Importance sampling according to the incoming radiance is much more challenging. The straightforward thing to do is to import a sample according to the direct component of the incoming radiance, which is called next event estimation. But this option quite often fails in most realistic scenes due to complex visibility. That is why in those cases, importance sampling the indirect component of the incoming radiance is really important. Since this is tackled by recent path guiding research, let's talk about previous work. Recent path guiding methods build different approximations of the incoming radiance field and use it to import a sample. More recently, research has shown that machine learning can be used to learn how to import a sample according to such approximations. We focus on two techniques that are closest to our work: the method from Borba and colleagues and the method from Muller and colleagues. The method from Borba and colleagues use a special cache and Gaussian mixture models for the directional component of the incoming radiance. They do a pre-processing step where they fill these two data structures by doing bidirectional path tracing. On the other hand, we have the method from Muller and colleagues, which uses a binary tree for the spatial component and a quad tree for the directional component. In their case, they do the training online while rendering by splitting the sample budget into increasingly longer iterations. This method has shown to be quite efficient and practical, and is inspiration for our method. Here we can see how the quad trees get refined in each one of the iterations to better approximate the incoming radiance. During sampling, the quad tree is used to generate samples. This is done with a hierarchical warping scheme proposed by Mack, Kulla, and Hardwood. The relative stored value in the quadtree determines the probability for traversal, and this process is repeated in the quadtree until a leaf node is reached. Within the leaf node, we sample uniformly. So we talked about how path guiding methods build an approximation of the incoming radiance, but what about the cosine weighted BSDF factor? Most path guiding methods use multiple importance sampling to combine path guiding with BSDF sampling. More specifically, in the original method from Muller and colleagues, they use either BSDF sampling or path guiding 50% of the time. Muller and colleagues later introduced improvements, one of which was an optimization step which chooses the percentage of use of each one of the strategies so that it minimizes the Kullback-Leibler divergence to the actual product distribution. Keep in mind that this mixing rate is optimized for each one of the special subdivisions of the SD tree. Going back at the rendering equation, we see that the ideal importance sampling strategy would sample based on the product of the incoming radiance and the cosine weighted BSDF. This is called product importance sampling. There are different methods that explore this idea, but the one closest to our work is the one from Herholz and colleagues, who introduced product sampling to the GMM technique we mentioned earlier from Vorba and colleagues. Keep in mind that this method shares the lengthy training step before rendering as the method that it is based on. Now let's talk about our method. In our method, we want to combine the efficiency and practical nature of the method from Muller and colleagues with the better sampling quality provided by product sampling. We do this efficiently by building an on-the-fly approximation of the product to use for sampling. As a preview of the results, we can see that the product sampling significantly improves noise, especially in scenes with glossy materials such as this one. So let's talk about what choices we had and the basics of our method. Since we expand the method from Muller and colleagues, we also use a special directional tree with 5 dimensions. The naive way to introduce product sampling would be to store the product explicitly. This would increase the dimensions of the data structure to 7, which would be too costly both in terms of performance and in terms of memory. The way we achieve product sampling is as follows. Given an intersection point in a 3D space, we have the quadtree, the corresponding quadtree, which stores the incoming radiance. For each node of the quadtree, we want to compute the integrated BSDF value, the integrated cosine weighted BSDF value. If we have this computed value, we can approximate the integral of the product with the product of integrals. This means that during the hierarchical warping scheme, we would just need to multiply the two values and use them for the traversal probability. Note that this approximation gets better with the refinement of the quadtrees. To compute this value, there are a few different options. First, we experimented with the Monte Carlo approach. For this approach, we built a temporary quadtree that has the same structure as the one that stores the incoming radiance. We generated n equal energy samples from the BSDF distribution and recorded them in this temporary quadtree. For 64 samples that we found to be a good compromise between performance and quality, this approach added a huge overhead of more than 10 times slower sampling. So let's see how we efficiently compute the integrated BSDF value. Our choice is motivated by the fact that a node of the quadtree is a spherical polygon in the sphere of directions. A very efficient method for computing shading integrals over spherical polygons is the method from Heitz and colleagues named linearly transformed cosines. This method allows for analytic integration of complex BSDF by using a pre-computed linear transformation that takes the spherical polygon to a cosine distribution where analytic solutions exist. This method is used in real-time shading, and our intuition was that it would be a great fit for our needs. In order to use the LTC method, first we need to transform the spherical polygon from the global sphere of directions to the local sphere of directions with a change of axis or a rotation. Here the surface normal is aligned with the z-axis. Then we can apply the LTC transformation that takes us to a cosine distribution. Here is the analytic expression proposed by Baum and colleagues that we use once we are in the cosine distribution. This breaks down the computation in a computation between each pair of vertices. You can see that this expression has still quite a few costly computation involving ACOS, cross products and dot products. Also keep in mind that this is computed 4 times for each one of the quads, and then for each one of the quads, so 16 times in total. And also this is done in the hierarchical warping scheme, so it's done recursively until we reach a leaf node. This unfortunately in our first implementations diminished the benefits of product sampling. So let's talk about the optimizations that we introduced to have better benefit from product sampling. To overcome this issue, we introduced optimizations in 2 main directions. First, precomputation, and second, vectorization. So let's start with precomputation. If in our expression for the analytic computation we omit the dot product with the z-axis, we get the vector form factor, which itself is a vector. Normally, we need to apply the 2 transformations that we mentioned to the polygon vertices and then compute this expensive expression. When the material is diffuse, then the LTC transformation is the identity matrix, so we are left only with the transformation that is an orthogonal transformation and takes us from the global sphere of directions to the local sphere of directions. For that reason, we can pre-compute the vector form factors for the first 5 levels of the quadtree and then apply the orthogonal transformation to the resulting vector form factor instead of applying the transformation to the vertices and doing all this expensive computation. This significantly improves performance for diffuse materials and materials with diffuse components. Here we see the gains for this optimization for our test scenes, sorted from the more diffuse ones to the more glossy ones. The results shown are the sampling cost for 64 samples per pixel in seconds. For our vectorization optimization, let's look at the computation that happens again in each one of the quadtree levels. Thankfully, this is a good vectorization candidate, so let's see how we computed this before the vectorization optimization. And here is after our vectorization optimization. As you can see, we compute these 16 pairs of computation at once in an AVX512 CPU using the Enoki library. Since this can be difficult to do without introducing more overhead, please refer to our published code for implementation specifics. Again, here are the benefits that we get from the vectorization and precomputation optimizations. You can see that we have a gain regardless of materials this time. So let's look at some results and comparisons. We tested our method in 6 scenes, and we compared against path tracing as a baseline, against the product GMM method from Herholz and colleagues, but for the 4 of the 6 scenes, since we had some issues with the training in 2 of the scenes, and against the method from Muller and colleagues, along with the later introduced improvements. We use a mean absolute error metric, and we average our results over multiple runs for each one of the methods and each one of the scenes. In our test scenes, we demonstrated on average a 15 to 20% improvement in noise for the same rendering time compared to the method from Herholz and colleagues. But still, the technique from Herholz and colleagues, due to its different representation and bidirectional fitting, demonstrates better performance in some parts of some scenes. As a result, in this scene, we show similar results on average. Compared to Muller and colleagues, with the improvements later introduced, we saw a 15 to 20% performance gain in noise for the same computation time. This is especially true in scenes with complex geometry and glossy materials. You can see more detailed results in the supplemental material of our publication. Like previous techniques, we saw an increase in average, like previous product sampling techniques, we saw an increase in average path length. And for that reason, we implemented a joint-based Russian roulette from Vorba and colleagues, which uses a pixel estimate to do efficient Russian roulette for path guiding techniques. We also mentioned that Muller and colleagues have an optimization to use the best strategy for each spatial subdivision between BSDF sampling and path guiding. Here you can see in red parts of the scene where BSDF sampling is used, and in blue parts of the scene where path guiding is used. In Muller's method, sometimes the generated directions are generated in the wrong hemisphere, especially in parts of the scene where it has varying normals. In our case, the normal of the surface is taken into account by the product, and as such we use path guiding for the most part of the scene. Finally, let's talk about some limitations and conclude the presentation. Our method's overhead increases linearly with the number of components. For that reason, components that have materials that have many components will benefit less from this product sampling. In addition, we don't guide materials with delta components. Also, our approximation with product of integrals has its own failure cases in theory. as you can see, if the two functions vary, they are very different from one another, like in this case, the two checkerboards, then the results are not as they have a big difference. But in all of our testings, we haven't seen such an issue. Also, I want to talk about some recent research, namely the robust fitting of parallax-aware mixtures for path guiding technique and the variance-aware path guiding, which both methods show that there is a lot of exciting and new things that we can still explore in path guiding. So this concludes my presentation. Thank you for watching. Make sure to check our code that is available in our project page. And thanks again for watching.
Thank you for recording the talk. It's a very interesting paper. We already have 2 questions in the Rocket chat. Sebastian Herolds is asking, I would be interested in the overall overhead of the product sampling for a sample compared to the method by Miller et al.
So, as I said in the presentation, the overhead is related to the number of components in the BSDF. So it's dependent on the scene. But what I can say is that, for example, for the bathroom scene, for the same time, 10 minutes of rendering, Muller and colleagues have 1,470 samples, and our method is able to render for 1,087 samples. So there's quite a big overhead, but still the quality of sampling makes up for it.
Okay. The next question is, in the jewel scene, some fireflies are still noticeable. Do you have an idea where they come from?
Yeah, so even with the improvements that Muller and colleagues introduced to the spatial directional tree, it still has some issues with approximating the incoming radiance correctly in some parts of the scene. And since we are also combining some renderings from the previous iterations, some of the fireflies that happen in previous iterations are hard to basically diminish. But I think it's mainly for the fact that in our method we assume a zero variance method, that in the limit the SD3 will be a perfect approximation of the incoming radiance, but that is not true. And that's why, as I said also in the concurrent work, the method, the path guiding, variance aware path guiding, Herholz was kind enough to run his code with our method, and he showed that it helped with the fireflies because they treat this variance head on.
Okay. A question from YouTube by Yuchen Wang. I'm curious why this method can do better in glossy scenes. Is this achieved by sampling more since we optimize with LPC vectorization?
So in glossy scenes, it works better because the BSDF starts to be more important in the rendering equation. And basically, then the incoming direction starts to play a role. So in those cases, Muller would solve and see if it's better to use the BSDF or the incoming radiance sampling. But for materials which are somewhere in between, their method still uses 50% of the time incoming radiance path guiding and BSDF sampling, while our method has the exact product to use for sampling.
I actually have a related question, perhaps. So you have this approximation where you separate the components of the integral and you assume separability, which is actually not incorrect in the leaves, because in the leaves, your radiance distribution is assumed to be constant, so you could factor it out. But as you move higher up in the hierarchy, this approximation can actually become worse and worse and cruder, and you know, this separability assumption. So I'm curious, did you try to see how much you are essentially losing, how much sampling efficiency you are potentially losing by doing suboptimal decisions early during the traversal?
Sure, yeah. So we had some tests where we basically computed this product in the leaves and then rebuilt the product from the ground up to have basically the correct values instead of doing this fasting. Sure, we are losing in sampling quality compared to this ideal scenario, but still the difference in performance was too big to even consider using it. And I would say that in the top levels, because the quadrants are storing the whole sphere of directions. So for the half of the hemisphere, the LTC is 0, and that itself is a really it's a really good value to have, to know that how we can produce directions in the correct hemisphere. And so this really helps the sampling compared to Muller and colleagues, where he sometimes is generating samples in the wrong hemisphere, and it stops the path tracing.
Okay, I was actually thinking about this bottom-up construction. I was wondering whether you tried. So it's great to hear that it's actually too expensive. Yeah. Okay. Lee Van Wu is asking, you have mentioned the limitation caused by product of integral, which is what we just discussed. So specifically, what were the failure examples where you would see this? I guess this manifests as increased noise. So can you actually...
Yeah, basically, yes, fireflies and increased noise. But still, as I said, doing it in the leaves was prohibitive in terms of performance.
Right. And is there like a specific scene where you would see this manifest more prominently?
I think in general, like more glossy scenes, we observed more fireflies in general. But yeah, there wasn't one scene where it like broke down. In most of our scenes, in the worst case scenario, we did as well as Muller, and in many cases better.
Okay. So we are about at the time for the Q&A. So Stavros, thank you very much for taking the time for answering the questions. I encourage the others to actually follow up in the Rocket chat and maybe discuss a bit more there. We will move on now onto the second paper in this session, which is, as I mentioned, in the context of real-time path tracing. It will be presented by Addis Dittebrandt, and he will introduce the paper title properly with all the co-authors in the talk. So we can start watching now.
Hello, I'm Addis Dittebrandt, and I present our paper, Temporal Sample Reuse for Next Event Estimation and Path Guiding for Real-Time Path Tracing. This work was created together with Johannes Hanika and Carsten Dachsbacher. With the recent advancement of hardware ray tracing capability on GPUs, ray tracing is now on the brink to adoption in real time. In fact, many working titles have now started to adopt this technique, because effects that previously relied on crude approximations cannot properly be implemented with this technique. Here, for example, we see screen space reflections being replaced by ray trace reflections. And the advantage is that out-of-view objects, such as the lights you now see in the helmet, are considered as well. Another option is to move to Monte Carlo methods, such as path tracing. This provides a unified framework for all kinds of effects, but it generally introduces noise. To offset this, offline renderers typically use high sample counts, but this is just not possible in real time. So there has been a recent focus on research in denoising techniques. The idea is that you take noisy images and apply post-process operations on them to eliminate the noise. And typical approaches, like the paper from Sheet from 2017, leverage temporal and spatial coherence for that. But denoising comes with its own set of artifacts, such as temporal lag and blurriness. Both are a bit exaggerated, and there has been work on mitigating these issues, but what we can also do is importance sampling. And that's exactly what we do. There have been a number of works starting to show up last and this year. For next event estimation, we have Moreau proposing light hierarchies and Bitterly doing extensive resampling to filter PDFs of light samples, both spatially and temporally. And for indirect illumination, there is Pantaleoni, who progressively learns light field approximations and applies it, for example, to importance sampling. We actually go in similar directions to the latter two techniques by exploiting temporal coherence to improve sampling over time. So we propose learning techniques. There's also a lot of work in the offline rendering community, but this is not easily applicable to real time. We therefore delegate to the related work section of our paper for more details. To give our high-level goals, we want to achieve learning for next event estimation and path guiding, and all of this should be done in real time. So much of the contribution actually lies on algorithms and data structures that execute directly and efficiently on GPUs. We also want to achieve unbiasedness and support all indirections, so we want to go beyond screen space. Furthermore, we want to support fully dynamic scenes. That means we can't really do much pre-computation, or if any, it has to fit within the frame time. So let's look at the Stanford Dragon right here. It is illuminated by these light sources, but some of the lights are simply occluded. With the visibility light cache, or the ULC, we use samples from the previous frame to extract the set of visible lights and then focus our sampling on just this set of visible lights. Now we have another surface that indirectly illuminates our dragon. Now the problem is that most rays actually miss it. And with the idea of the compressed directional quad tree, we guide our rays towards this indirect surface, but with a very compact representation that is tractable for real-time usage. Now the problem is that both of these techniques have high spatial variation, so we have to use multiple ULCs and CDQs for the entire scene. And for that we use an octree structure in which each leaf node contains a ULC and CDQ, and it is adapted temporally over time so as to account for dynamic content. And finally we go over the evaluation. So let's first begin with the visibility light cache. So here we have an example scene from Quake 2 RTX. We can see that there are quite a lot of lights, but they only really illuminate a small portion of the scene. So if you look at the point, we can see that it is only illuminated by these light sources. So what if we explicitly focus our sampling efforts on just them? And that's the basic idea of the ULC. But how do we get to the visible lights? As mentioned, we leverage temporal coherence for that, and we have already drawn visibility samples in the last frame, and we can use them to extract visible lights from the set and importance sample it. Of course, this is imperfect because occlusion is a very complex problem, but with enough samples, we've shown that this is still feasible, actually. Another problem is that new lights are never sampled by this technique because it just samples what is already known. So we need a secondary strategy for that. We call this the exploration strategy, and this is discussed in more detail in the paper. Just as a side note, what we do with our implementation is that we stochastically sample either the ULC or the exploration technique when sampling a light source with a given fraction. We have tailored the ULC for efficient importance sampling and PDF computation. And there are quite a few trade-offs that we had to make this efficient. For one, we store all the lights belonging to a ULC in a linear array, which is furthermore divided into a variable number of buckets that each have a fixed capacity. In this instance, a capacity of 3. Practical ranges range from 60 to 32. The lights are then distributed into the buckets according to a hash on their identifier. So there is a deterministic relationship between light and bucket. We can then select a bucket with uniform probability and importance sample a light in the bucket. For that we use the unoccluded contribution as importance measure. For point lights this is actually simple enough because we can directly compute the contribution. And at least for area lights, we now have linearly transformed cosines with which we can at least approximate the full contribution. So that's also possible. Note that while this measure is an unoccluded importance measure, the ULC itself tracks all the visible lights, and therefore visibility is accounted for implicitly. So we get quite good sampling with that. Well, the problem is now that iterating over this bucket structure is linear in time, and that's why we have the bucket structure in the first place, to bound computation time. And of course, having more buckets means higher variance, more noise, because we make uniform decisions. Here we see the effect of the bucket size of varying the bucket count indirectly through reduced bucket sizes. And left we have bucket size of 2, so the noise is very visible, but as we increase the bucket size, things become much better. Of course, this is highly dependent on the number of light sources that locally influence the region. To give details on the construction, now we have given the light samples from the previous frame. These are here encoded by color, so light identifier is encoded with the color, and out of it we want a ULC. The idea is that we now duplicate the samples through bucketed hash table. So now we have the unique lights at our hands. And the thing is, if we have used the same hashing function as the ULC, then this hash table is already some kind of ULC. The only problem is that the number of buckets is super conservative. So the resulting sampling quality will be very noisy if we use it as is. So what we now do is we merge it in a bottom-up fashion while the capacity constraints are still upheld. And eventually we'll have our final ULC that we can use for important sampling. This concludes the visibility light cache. We now continue with the compass directional quad tree. The idea is that we map directions into a 2D space. Here we use octahedron maps, but really anything can be used. And in this 2D space, we have a structure that assigns energy to its subregions. And we can use this structure for important sampling. In our instance, we use a quad tree. And this idea is directly based on the paper from Müller from 2017, but we can't really adopt it to real time without any modifications. The problem is, for one, that it has quite a large memory footprint. Each quad tree has to be stored. We have one quad tree per octree node, and the memory footprint of each quad tree is quite large. So we need to store explicit topologies and the weights for the stochastic traversal, and that becomes quite huge. So to mitigate this, we store the topology in implicit form using a rank and select data structure. So this brings down practical topology sizes with 96 leaves or 97 leaves down to around 128 bits, which encodes to 4 integers, which is not a lot. The weights are completely removed. We instead assign a uniform weight to the leaves. So in this case, importance is completely encoded within the topology. And we do a bottom-up traversal to reconstruct the position of a leaf for important sampling later on. Now this structure is much more simple, of course, compared to the original. It's not comparable in terms of sampling quality. But we show that it still provides useful improvements and is actually tractable in real time. Another point is the adaptation scheme. They use a geometrically growing sample count for refinement, so you double the sample count each iteration. This is not possible in our instance, but since our quad tree is already much simpler, we can revert to a simple per frame adaptation. And in our case, we just split one leaf node and collapse another one. So we do one simple modification to the existing quad tree, but we'll get to that shortly. To give an intuition on the implicit form, we have a breadth-thirst encoding of the tree. Each bit decides whether a node is an inner or leaf node, and the levels themselves are stored in succession due to this breadth-thirst encoding. And with the rank and select operations, we can efficiently compute the parent and child relationships of each node. And that is in particular used for importance sampling. Here we show an example. So as mentioned, we uniformly select one leaf node, and then we have to reconstruct its bounds. For that, we use the bit position with regards to bring it with regards to its parent frame. So in this case, it's the second bit, so it goes to the upper right. And then we traverse the parent structure and do basically the same until we reach the root node. And this way we have reconstructed its position in the 2D space and can convert it to a direction afterwards. Now we also need to adapt the structure towards high energy directions. What we have given is the previous quad tree from the previous frame and samples. In this instance, they are not lights, but directions that each have assigned some form of energy. What we now do is distribute and accumulate these samples among all the leaf nodes. And we select the leaf node with the highest energy and the node with the lowest combined energy and swap them out if the leaf node has more energy. Of course, this happens over multiple frames, so we need to look at how this converges over time. Here we see the convergence behavior in the initial state, at least, in the converged state. The CDQ is sampled at 50% probability and the BRDF still at 50%. and now we reset the state, and we see there's quite a difference, but over a few frames it reconverges to this stable state, and we get relatively nice sampling again. Of course, this is still far from perfect, but a significant improvement over the initial state. This concludes the compressed directional quadtree. We now go the temporal sample adaptive octree. So for that, we had quite a few requirements in mind. For one, we want, of course, to do efficient point queries with the structure. So we efficiently want to get to the ULC and the CDQ for a given surface point. It has to be a completely dynamic structure, so it has to adapt over time to new situations and be usable for the indirect bounds. So that's why we have a word space structure and an octree structure for efficient traversal. And this scene shows a visualization of the octree. The leaf boundaries are projected onto the surface as represented by the green lights. It is completely dynamic as mentioned. In this case, we see it adapt to player movement as surfaces get closer to the camera. Of course, moving objects such as this enemy right here are also handled. Yeah, in general, the problem is, of course, that this is a very rigid subdivision scheme, so it isn't always a good fit for non-axis aligned surfaces. But we delegate to the paper for more details on how we mitigate this, at least with the visibility light cache with our neighbor merging scheme. But yeah, there's no time for that, sadly. We adapt our octree with a simple split and collapse scheme. So we have thresholds based on the observed sample counts. This is quite a natural fit since we already use these samples for adapting the ULC and CDQ. And the ULC in particular is very dependent on having a high enough sample count available to produce a stable cache. We there also use an hysteresis approach. This is especially important for indirect illumination because, of course, the rays don't land everywhere uniformly. So we instead use an upper and lower threshold when dividing the quadtree. So you see this delayed response as a result in this scene. But yes, that's so far of the octree. Let's now finally continue with the evaluation. Now we have shown some things in line with the presentation, but we've also compared, of course, our approaches against existing techniques. All of this is implemented in Quake 2 RTX, as you may have noticed. The ULC is compared against the light hierarchy from Moreau from 2019 and against the static light lists that are part of Quake 2 RTX. That's a pretty similar technique, except that it relies on static clustering in the scene on a BSP structure. We are completely dynamic on the other hand. The CDQ is compared only against BRDF sampling for lack of different techniques that execute in real time. But of course, we now start to see other techniques surfacing. So comparisons in this regard would be quite interesting, actually. But yes, we will only show an example comparison of our light sampling techniques of the visibility light cache against the light hierarchy and static light lists. Here we see an instance where the visibility light cache is on par with the static light list approach, but much better than the light hierarchies. Yes, often the static light list captures visibility pretty much as good as the visibility light cache, but keep in mind that we are still completely dynamic and the static light list relies on the BSP structure to account for spatial variation. In some instances, this plays actually off, so the static light list can be better because what we still have to do is our exploration sampling. We need to find new light sources. So in this case, we have a situation where our exploration strategy, which induces more noise because we still sample it with a given fraction. So in this instance, the static light lists performs better, but we're still better than the light hierarchy approach. Here's a test case where the visibility light cache outperforms the other techniques. To give a few figures on the performance readings, on the left side we see the pre-processing time of our approach, and on the right we see the path tracing time. Those are our timings over multiple frames in milliseconds. Pre-processing generally takes around 1 millisecond, but at least with our configuration, so we have a split threshold of around 2000 and 1000 nodes as upper and lower threshold. So this will certainly vary the more you vary the thresholds. On the path tracing side, there is certainly an increase in execution time of our techniques, at least compared to the light hierarchy approach, and given our bucket size of around 32 with which we evaluated the scenes. It is on par with the static light list approach. That might tell us that it is not really problematic to the octree traversal, because both approaches still have to sample the lights themselves, but only the visibility light cache has to also do all the traversal stuff. And the CDQ adds another 2 milliseconds of execution time. So yes, those are certainly significant readings, but they are all within interactive rates. To conclude this presentation, with the ULC, we do high-quality next event estimation through explicit tracking of light sources, and we therefore handle visibility implicitly. With the CDQ, we propose a path guiding technique that is actually tractable for real-time usage and still provides actual improvements. And the octree is a structure that we propose that is needed for spatial variation. It automatically adapts to new scene situations over time and is quite efficient at that. There are still some caveats to be aware of. For the ULC, for example, we have quite limited scalability with regards to the number of locally influencing light sources. For that, we certainly need some kind of aggregation scheme so that we don't handle individual triangles. We also experience increased noise levels with the CDQ for the case of specular BRDFs, because the response is just so specific. So for that, we need some kind of product importance sampling scheme, which can be pretty challenging. Oftentimes also the spatial resolution of the octree is just not enough, and we don't have enough samples at our disposal, among 2 million at 1080p. So what we have to do is to do some kind of temporal increase of samples that can be used for the ULC and CDQ. Thank you for your attention. I now await your questions.
Okay, we are back. Thank you, Addis, for recording this talk, and congratulations to a very interesting paper. I do not currently see any questions in the Rocket chat, so I will ask a few that I prepared for this. So you have this visibility light cache, and then you have the CDQ, the other data structure for important something in direct illumination. These are very different approaches, actually. But have you tried to compare them on the same type of illumination? For instance, have you tried using both for direct illumination and see, compare the strengths and weaknesses?
I wouldn't really recommend using the CDQ for next event estimation. I've tried turning off like next event estimation and rely purely on the CDQ, but it is like way too imprecise to handle like this, to handle like pure lights for that regard. Because you typically just land on spots that are besides the light sources. Sometimes you land on the light source. And with the CDQ, you also have this positional dependency. Because like we have our octree regions, and sometimes if you're like on the border of this octree region, it is not precise enough. On the other hand, with the ULC, we have like precise vertices that we can sample with next event estimation. So I wouldn't recommend it to use it for the CDQ, to use the CDQ for next event estimation.
Okay. Carl Lee is asking, first of all, he's saying very cool work, and then he asks, I'm curious about how easy or hard it may be to extend this technique to handle infinite light sources such as IBLs, environment maps, directional light sources, and so on. Especially considering that the VLC considers finite distance from light to camera as part of the heuristic weights.
Okay, I have to think about this for a second. To extend this to handle infinite light sources. Okay, so we assume we have like a directional light source like the sun. I think this can be explicitly handled. I mean, you need like a branch on the type of light source in this instance. So you handle triangle emitters differently compared to directional emitters. But in this sense, visibility is you can still learn visibility for directional lights. If I don't have it wrong in my head right now. I don't know if that answers the question already.
I encourage Carl to follow up on the Rocket chat, and then I will try to read it if there is any follow-up.
Okay. not sure if I got it entirely.
Let me ask a different question. So do you think in this application of real-time path tracing, with your current data structure for the indirect elimination importance sampling for the path guiding part, do you think you are limited by the information that you can extract from the individual samples, or by the data structure that, with all the constraints of real time, it needs to be fast, easy to update, and so on? So what do you think in this application is the more limiting thing? Like, is the data structure prescribing what you will do, or using more advanced data structures doesn't make sense because you have so little data in the samples that you actually need to regularize that heavily, and this is enough?
I mean, I do have problems with the number of samples. Like, the octree resolution is oftentimes simply not enough, especially for the CDQ, because it has like this high positional dependency. So ideally, I would want to have super small octree nodes. But that doesn't work out. You need like thousands of samples in this instance to adapt the structure, or at least the way with the current parameterization. So I would currently say that the sample count is more or less the limiting factor right now. We would need like some sort of temporal approach. I've talked about this shortly in the conclusion, like that you can temporarily increase the sample count in the octree structure, or at least that you accumulate in the CDQ your contributions temporarily over time, so that you get a higher effective sample count, a more stable estimate for the directional information. And that might improve things at this point, but we just don't have enough samples for single frame with a single frame. I hope that answers the question in some way.
Yeah. Okay. Thank you very much for answering all our questions. And again, congratulations to a great paper. We will now move to a slightly different context from real time. We will switch to movie production, and we will have Alejandro Conty and Christopher Kulla talk about adaptive caustics rendering in production with photon guiding. We have both of the authors on the line for Q&A afterwards, so stick around. Let's go ahead.
Hello, everybody. My name is Alejandro Conty from ImageWorks, and I'm going to present the system that we are using to render caustics in production. Now, if you're listening to this, you're probably familiar to the term, but this is basically indirect lighting that comes from very smooth surfaces like glass or metal, and then is projected onto close to diffuse surfaces, and it's very hard to do that with a pure path tracer. The most common use for us is water scenes, but not just that. There's also caustics, very common too, and other glass objects and cases like this. But algorithms for rendering caustics have been around for a while. Ever since photon mapping in the 90s, there's bidirectional methods, there's VCM, metropolis light transport. All these methods can robustly handle all kinds of light interactions very well. But we haven't been very lucky applying those in production. They're very slow because they trace too many rays that in the end are not useful to the render because they are ignored by the MIS. Also, there is little control from the artist to cheat, to do light filtering. Many tweaks that are used commonly in production are not possible with these integrators. If you are using a metropolis method to improve the convergence, you're going to get a splotchy look, which is normally not welcome. So after many attempts, and there even a few shots final with caustics in a couple of shows, we thought, okay, so next we're going to try just photon mapping, and we're going to use it only for caustics and in isolation. So this is because our render in production is a big piece of software. It has many features, and we need the integrator to be as simple as possible. We need it to be predictable, and we need it to be flexible. And with the incoming GPU wall, simplicity now is more important than ever. So we thought, okay, our render, it's already rendering passes, refinement passes, so it makes sense to have a photon shooting stage before every pass to compute the caustics. This is much like progressive photon mapping, but it's going to be constrained. It's going to be used only for certain lights, certain objects, and only for caustics, and leave the rest of the render to the path tracer. So the main goals were these. We needed to be guided because we want to reduce variance as much as possible. And since we don't like metropolis methods, we're going to go with some learn PDF, some table to improve it. And it's going to be on demand. That means the artist is going to choose which lights and which objects are going to cast caustics. And finally, it's got to be adaptive. That means that we are not going to ask the artist to select the number of photons to shoot over the scene. We're going to have a system that it just keeps rendering until the noise is gone. That's the idea. They're just the same as path tracing, which is the soul of our render. This, in the drawing, is a render pass. Up until now, there was only path tracing, the one in the center. Now we're adding these extra parts around it. The first is a photon emission stage that uses a guiding table to create a photon map. And then we jump into path tracing. And path tracing works as usual, but in addition, it's going to make lookups in the photon map just for caustics, and at the same time, it's going to integrate, it's going to render another signal, a visibility signal of the photons. And once path tracing is done, we get to update, to compile the visibility, to update the guiding table that we're using, which is the only thing that survives from render pass to render pass, because the photon map is always new. So we're going to explain what are these new things that we're adding. And the first is the guiding of the photons. Remember that this is on demand, so the artist is choosing the light sources and the object targets. So that's already helpful, because if you have a very small object casting caustics in a very big environment, just choosing the object is going to narrow down the directions, the photon emission quite a bit. But that's not all. We still need to do more. We still need to choose a light between the selected lights and choose an object between the selected objects, and more importantly, a direction to shoot the photon. So the idea is that we're going to do that all with just one table. So, and that table will be the domain, the space over which we are going to compute the visibility, which then translates into a PDF. From the table we get it, from the visibility signal, we construct a PDF. The PDF and the photon count is going to determine the density, in other words, the number of photons per solid angle unit, and this lets us estimate the photon spread. That's when we shoot a photon, we know how the radius grows along the path until we store the photon in the photon map, and every photon is going to have a different radius. This is the merging radius, and it's very important for our learning process, because on a usual photon map, on a usual photon system, what you do is you search for photons which are just plain points on a radius, and with that you make an estimation. But our photons are spheres, so what we do is we search for all the spheres that overlap the shading point. That's going to define also the visibility signal, which is basically the throughput of the photon over the probability of in this case, over the probability of shooting the photon towards that direction. And that's what gives us the visibility signal. This is just one more Monte Carlo estimation with a very strange projection, which instead of projecting to camera, we're projecting to the cell the photon came from in the guiding table. That means that tables in the cell with very high probability will have will have many small photons visible by each of them visible by just a few pixels, and the low density cells will have big photons that are going to be visible by many more pixels, but they're going to be fewer. So one thing compensates the other and the signal stays stable. So what does this table look like? Well, we could start simple. We could have, like, for instance, let's imagine a scene where we just have 3 lights and 4 objects, that is 3 caustic lights and 4 caustic targets. So we could just build a 3x4 matrix, a probability matrix for choosing the light and the target, right? And then you will have to uniformly sample the direction towards the target. But we can do better than that. We can expand this matrix by some fixed resolution like you see in the drawing on the upper part, and we create a bigger table. This table will let you choose not only the light and object, it will also choose a cluster of directions which narrows down even further the direction you're going to sample. This is much better, but still is not optimal, because some light object pairs are going to be more important than others. So fixed size doesn't work for us. We prefer a table where the subtables are of variable size, like in this drawing on the bottom. And this is what it looks like. If you have a simple scene like this, just 2 spheres and 2 lights projecting caustics, on the right you get the guiding table. If you were expecting some kind of rounded shape, well, these tables run on random numbers who have a strange mapping, and it deforms the appearance of the object. This is what it looks like. Or in another typical case, if you have a big water surface and just 1 light, the guiding table looks like that on the right, which basically lets you see the camera frustum. And this is a more complex case from production. It's something that I didn't have to ask clearance for, but you can't really tell what the scene is. You just see what's the importance of the photon emission directions. So let's look into how do we sample this table to produce a photon emission direction. This table is sampled just like any other 2D CDF. By row and column, you select a cell, right? And that cell is going to live inside of one of those subtables. Though that subtable is going to tell you which light and which object, but also what direction, because the difference of this sampling is that we are not wrapping the random number to the cell. No, we are wrapping the number to the whole subtable. That gives us 2 new random numbers that you can directly use to sample a direction on the cone emission towards that object. And that's it. That's how we produce the photons that we shoot into the scene, right? So we are now in the stage where we are already rendering and we have to look at the photons, right? So we estimate irradiance on the surface gathering. If we estimate the irradiance on the surface gathering and saving all the photons within a radius, we are introducing a blur. Even if we use a pixel size radius, it is still a blur, a low pass filter. So instead of doing this, we're going to randomly select 1 photon based on some useful measure. Here is proportional to the inverse square radius and the throughput. That's going to eliminate the low pass filter, and the image is going to be noisier, but this noise is the kind of noise that we are looking for. Just look at this picture, this scene. This is an inset of a caustic scene. On the center, you have the regular photon mapping result, which is gathering all the photons on the radius, on the pixel size radius, and shading all of them. As you see, it's blurry, but it's noisy as well. I mean, it's low frequency noise, and the problem with this noise is that it's easily confused with features. It's not going to be addressed by the refinement, and it can't be denoised properly. So instead we compute the image on the left, which is the same thing, but we are just picking one random photon for sailing. As you see, that's noise here, but that's high frequency noise. And it can be refined to the picture on the right, which is really what we're looking for. You could also denoise it and get a much better result than the one in the middle. So this is what we do with surfaces, and with the volumes we need a similar trick. But the volumes are different because we are using photon beams, and our photon beams are being processed as with a 1D beam estimator. That means that they are basically ribbons, right? The width of the ribbon is going to depend on the sampling density. These ribbons are going to be ray traced, which is expensive. So we can't do exactly the same thing like in surfaces. We can't collect all the photon beams and then randomly selecting one. We need something more greedy. So we are going to do two things. The first thing is cutting off distant beams, and the second thing is randomizing the beam width. For instance, the first one is cooling distant beams. So you have a ray going into a volume of beams, like you see in this drawing. It can be many beams, right? So what you're going to do is sample a distance limit based on the extinction. And once you have that limit, you discard all the photon beams beyond that distance. And for the rest, you merge them, compensating, taking into account the probability of not pruning that beam. That's going to save a lot of work, especially on deep scenes, like this one. This render is much faster thanks to this risk, thanks to this trick. But the problem still remains unsolved because this method is very clean. It produces very little variance, so it's still not there for us to refine adaptively, because the real source for bias when working with photon beams is the photon beam width. That's it, the one that comes from the ray spread, the photon spread, right? If the photons are too wide, it's going to be blurry, right? So what we do is randomize the width from the pixel width, which is, let's say, less bias, to the photon beam, to the photon spread width, which is very biased. And we do that with this method using the square root of the random point. And we do that just to get the appearance of a triangular kernel. But you may ask, oh, and why going through all this trouble? Why can't you just use a pixel size width, right, like we do with surfaces? Well, we don't do that because it looks awful. If you look at these pictures, the one on the left is rendered using pixel size width. You see that laser beam line artifact thing is horrible, and it takes a long time to go away. If you start doing this from the beginning, from the first passes of the render, when there are fewer rays, it's pretty bad and it's very distracting. And also, more importantly, it looks like a feature. The artist might even think that the render is broken, right? It's not going to converge, it's not going to refine, and it can be denoised as well. Or if you use the spread-based width, like in the middle, you get the blurry bias look, which is also what we don't want, because that thing also looks like converged. The render is not going to refine that. A denoiser is not going to do anything with that. So we do the random width trick, as you see on the right. That's the type of noise that we're looking for. That kind of noise, the render identifies like unconverged noise, and is going to address those pixels and is going to render adaptively to this picture. And it converges because the beams get thinner and thinner as the density grows, right? And by the time they reach the pixel size, the line noise is not visible anymore, so it looks good. And this picture doesn't take forever. It's just 20 minutes. And now I'm going to show you a case with heterogeneous medium, a little animation. You see how we also handle this case. I'm going to play it again. Let's play it again. It's more expensive, of course. It takes like close to an hour per frame on 12 cores, but it's working fine, right? So in summary, our experience with this method has been that the artists are very happy because it works out of the box with almost no setup. The default settings just work, and the advantage is that they can cheat if they want. They can choose which light. They can have a special light for caustics, only for caustics. They can do many tricks, and the render is fast. That's very important. All the filters work, light linking works, and for us in the Arnold team, the engineers, we like it because this solution lives in the code in a separate, isolated file with very few hooks on the main path tracer. That's very easy to maintain, and the render times are good. Like we can get volumetric caustics between 15 and 30 core hours, which is very good. Like this sample, for instance, this is as close as a production shot that I could show here because I couldn't get clearance for ongoing productions. But this is pretty close. It's just using a public domain model, but the setup is the usual water simulation, underwater scene, underwater shot, and actually production lighting like. So this render is working in 15 core hours, which is very good for a volumetric caustics. And that's a very good result still. Well, there's, of course, open problems to solve. We would like to be smarter about the photon count when the refinement just leaves a few pixels to be worked with. We would like to have maybe a more adaptive guiding so we can work with bigger scenes. There's also the acceleration structure that we use for photon beams is a simple BBAs. That means that we have to split the beams for it to be efficient. That wastes a lot of memory. So that's something we would like to address next and improve. But this is it. Thank you for listening. I invite you to check out the paper for the details. We are here.
Okay, we are back. Thank you, Alejandro and Chris, for submitting this paper, and congratulations on the great work. I will jump right into the questions. Rocket. So there is one by Benedict Bitterly. Is the distance-based beam culling based on the short camera beams, track length estimators, essentially by Jaroslav Krivanek and colleagues, or is there a difference?
Well, I'm not sure I understand what the short camera beam track length is, but it's based on the camera array or viewing array, because these are also visible on the indirect. It's just what the render would use to render the resulting pixel.
Yeah, so I think it basically does. It's basically the same thing. Yeah, we're basically sampling the transmittance to find out. Yeah.
Yeah.
Okay.
If the median is heterogeneous, well, there are many solutions. We're using a biased tabulated version for that, so that's specific to our render. But other techniques are possible as well.
Jakob Munkberg is asking, which denoiser is used together with this approach? Are there any specific requirements on the denoiser?
We are using the in-house denoiser, Sony Pictures ImageWorks. It's called Spotless. And it's just taking like the usual denoising inputs like albedos, texture color, surface color, normals, things like that. That's pretty much, it hasn't been modified specifically for photons.
Is it based on, sorry, go ahead.
Yeah, I was going to say it's a traditional denoiser in the sense that it's like, filter based and just looks at patches of the image and aligns them with features and works that way. And it just uses the image space variance as input.
Okay, I actually have one question myself, or maybe two questions regarding the atlas that you are using. Is it actually needed, the atlas? Couldn't you just have like 2D textures of different sizes laid out somehow in the memory? Or do you actually leverage somehow the nature of the atlas, that it's all in one 2D texture?
Yeah, that's a good question. Well, the first motivation was that we wanted the method to warm up very quickly. So using a heuristic to size the kind of just to allocate the space for some pairs based on importance would help to quickly convert the learning. And the other reason was because it's very easy to output this to an EGSR for checkpointing and debugging. We have an AOV during the render that you can look at and see how the guiding is learning. But like I said in the last slide, we are thinking that maybe it would be good to explore other approaches like an adaptive quad tree, like refining, like splitting where needed. Just one more thing to explore, but this is the first approach we tried actually. So a lot of follow-up to do there.
Ali is asking, I'm curious what the rationale for tracking separate light object pairs in the guiding table is, as opposed to just building a single guiding distribution over, say, the 0-1 square unit square for emission directions.
Well, the reason is that in some cases, like for instance, let's say you want to have eye caustics in the middle of a scene. The eye is a very small object compared to a very big environment. So it's going to be much easier if you start with the cone that joins the light with the target object, in this case an eye. It's going to converge much faster. If you just sample all the sphere of direction, imagine that you have a point light source, it would be much harder to find the target. That was the reason for this approach.
Yeah, the other motivation for wanting to specifically select individual objects is that artists typically are only interested in very specific caustics in the scene. They don't actually care to get like a global solution of all possible caustics. They say, I want this water to produce caustics, and if there happens to be something metal or something else in the scene that might theoretically produce a caustic, they may not actually want that. So being able to be very selective is actually desirable in our case.
So your decision to actually go this way rather than using the other methods, which you actually mentioned in the paper that you had them implemented, and it was just the overhead didn't pay for it, and maybe it was not as expressive as you would like. It was really driven by the artistic control. Is that correct, or more by
definitely.
Okay. And so that just brings me to another question. So with great control comes great responsibility. So do you have anecdotal stories from production where the artist used it in a wrong way or in a way that you didn't anticipate, and then it led to crazy rendering times?
I would say that so far it's still relatively new in terms of like making its way into production. So we're still kind of helping the users when they need to, and they think of it as a fancy feature still. So they're still very cautious when turning it on. But I'm sure.
The artists are very used to fake caustics using like a slide map, something. So when they use this feature, you come up with questions like, what the hell is this? Because they're not getting what they expect. Like they're not used to thinking of light bouncing and projecting things, and they get shadows on unexpected places, and they get very surprised. So the tool is new. It's a little bit confusing. So as Chris was saying, you only want caustics from this particular object, because if you start getting caustics from something else, the artist is going to be surprised, like, what is this? I don't want this. We are already getting those questions when you select the object. So it's
Right. Okay, this is an interesting discussion, and there are more questions actually in the chat, so let's follow up there. We are unfortunately out of time, so I'd like to thank all the authors who presented and congratulate them again to their papers. The next session, which is about global illumination, starts right away, so just switch to the other session on YouTube, and let's keep enjoying EGSR this year.
Thank
Bye.
you. Bye.